Alright, welcome to the last section of this unit. This is section 10.1 on human hearing. So we're going to have a quick overview look at what components there are in the human ear and how those parts work together. So let's get started. So we're going to start on the very outside, the pinna. Acts like a funnel for sound, so you can see different animals have different shaped pinnas. Dogs can rotate theirs, those types of things. Ours is the way it is. We have a slightly forward facing, so we hear sounds in front of us a bit better. We do have a range that we can generally hear as humans. It's usually from 20 to 20,000 hertz, but what you'll find is most of what we hear is about 1,000 to 5,500 hertz. Okay, and the auditory canal is the little part where you'd stick your finger. Don't do that if you have long nails, and especially don't put a Q-tip in there. We'll talk about that in a minute. And there's a bit of a magnification by going down that canal, okay, of the sounds you hear. So that was the outer ear. So now if we start to move into the middle of the ear, this is where we have the tympanic membrane is your eardrum. Okay, the fancy name is tympanic membrane. What you should know about the eardrum is that it's really, really thin, 0.1 millimeters. Okay, it's super sensitive. You have to be very, very careful with your eardrum. One of the reasons why you shouldn't use Q-tips, or if you do use Q-tips, you should never go very far into your ear with them, is that because it's so thin, you can damage it, you can puncture holes in it. It's painful to damage, so be very, very careful if you have long fingernails and you're scratching your ear or anything like that. You do not want to damage the eardrum. Okay, and we're going to go through what all of these things do. It has a little muscle attached to it so that it's always kept taut. And then once you get into the inner ear, you have a sort of more of the biological, chemical, electrical features that are happening with your hearing. So the key piece that you may be familiar with is the eustachian tube. If you've ever gone and had a sinus infection or a cold or something and you feel like your ears are plugged, it's because there's issues going on with your eustachian tube. If you've gone into the deep end of a swimming pool and swam down below and your ears hurt, okay, well, that's pressure building up on the outside of your eardrum and it's not balanced with the inside. You can do something called the Valsalva technique, where you plug your nose and you try and blow out through your nose, and it raises the pressure inside the eustachian tube. That balances the pressure of the water pressure acting on your eardrum, and it tends to alleviate the pain. It's the same thing if you're flying on an airplane and you feel that pressure. You can do the same technique. It'll help balance. Yawning, swallowing, chewing gum, those types of things will help balance that pressure. Okay, so how do you actually hear? Okay, so we talk about sound waves, their compressions and their refractions. They're oscillating particles in the air. And you can see from this picture here, and I have a couple of really good videos you can watch shortly. The sound waves come down your ear canal, okay, as refractions and compressions. They get to your eardrum and they stimulate your eardrum. So your eardrum is just like the head of a drum, okay, and it will move back and forth. So a compression will push the eardrum in, a refraction will pull it out. It's not really pulling it out, it's just the way the pressure works, because you have a lower pressure on the outside, so the eardrum will tend to move outward. And that action of moving back and forward is what's going to stimulate the inner part of the ear into action, and that's where we're going to start to get the electrochemical effects of how you hear. Okay, so as you move inside your ear, this is where some of the three smallest bones in your body are. Let's just get this up here. So I will not ask you to memorize any of this. This is not biology, but the hammer or malleus, so mallet, hammer, those are usually pretty easy to keep together. The anvil or incus, and the stirrup or stapes. Okay, so these are the three tiniest little bones in your body. It's a mechanical system. The way they work together, they end up actually amplifying or increasing the pressure variations by a factor of about 20-ish. Okay, so what you hear, that pressure comes in, and then those little bones, the way they're oriented, increase the pressure. And they do that because they're going to then push on another membrane called the oval window. And the oval window is attached to something called the cochlea, and we'll look at that on the next slide. Okay, so you have, just to recap, you have sound waves coming in they stimulate the eardrum. The eardrum makes these little bones move. Those little bones are connected to the oval window, and they make that pulse back and forward as well. Okay, so there's a lot going on when you're hearing things. Okay, so the cochlea is a little snail-like organ. It's not a snail. I'm telling you right now, so if that shows up on a quiz somewhere, I get people every year. It's not a snail. It's not called a snail, so just I've warned you. Okay, it just looks like a snail, but it's wound up. It's wound up into a little snail-like shape because it takes up less space this way. It's a fairly long little organ, not organ, but piece of your body. Just like your stomach is woven back and forth, it allows for a greater surface area, and you can fit more of what we have inside of it, which are called basilar membrane. They're little hairs. These little hairs stick up. Okay, and they are the sensors that are going to turn mechanical motion into electrical motion, or sorry, into an electrical signal, so that your brain can understand what's going on. Okay, so there's a lot going on inside this. These little holes right here, this is where that window, that oval window, these guys right here are attached to the cochlea, so it would sit right on here. Okay, and as that oval window pulses, it transfers some of the frequencies down into the cochlea, and then these little hairs are attuned to different frequencies. So for example, a 200 hertz frequency won't make the hairs move, or the basilar membrane move inside, okay, until it gets down to where those little hairs are that are attuned to 200 hertz. Okay, there are two really good videos here. Please watch them. This one is sticking a camera in someone's ear. In fact, it's a doctor sticking a camera in its own ear, and you can see what the canal looks like. You can see the eardrum as well. Okay, and then this one is a digital version, a bit of a storytelling of what I'm going through with you right now. Both are really good. Please watch them. Okay, hearing loss. Just a quick comment on hearing loss. Moderately loud sounds do not damage your eardrum. Okay, so things you have to be worried about, and you can read this on your own. If you have ringing in your ear after a concert or after you're listening to music, what you really need to know is that you have done permanent damage. Okay, so as a young person, if you like your music really loud, beware that if your ears are ringing afterwards, you've done damage. You can have some surgery to fix the physical parts like the eardrum, the three little bones, those types of things. But if you damage the cochlea, you're in big trouble. Okay, so the little basilar membrane, the hair cells inside there, if you damage those, then you have permanent hearing loss. Okay, now there are some features or some things out there that can help. There are hearing aids, and hearing aids are basically little stereos. They have a microphone, an amplifier, and a speaker. Okay, so they pick up the sounds around you. They amplify them so that your damaged ear can get some sort of a signal to try and process. You also have something called a cochlear implant, and that skips some of the physical parts, the little bones, the eardrum, but it's a little more invasive, and it's only if you have really serious hearing loss. And again, I'm going to leave most of this for biology people. Oops, jumped forward here. So this is what they could look like. Modern hearing aids are really hidden and tiny now. There are different forms. You have ones that plug the auditory canal. You have ones that sit over the back of your ear. They have little volume controls on them. Okay, so they're just like little stereos essentially. Okay. A cochlear implant's a little bit more invasive. You can see that it's actually a transmitter and a receiver. Okay, it's mounted to your skull, and you can see this wire right here. Okay, coming all the way down to your cochlea. Okay, so that's a much more serious intervention to help you with your hearing, but there's things that are out there. So this is a summary. I'll leave you to read that. What I want to focus on is just this, because to me this is absolutely phenomenal. This is what's going on as you listen to this video. So you have air that's vibrating, particles. Okay, that's the sound that enters your ear. Okay, and there's a whole bunch of other things that happened before that with speakers and etc. But this is the journey of sound in your ear. Air vibrating particles, membrane vibrations, so that's your eardrum. It then moves to mechanical motion, which is your three little bones, and then it goes back to a membrane vibration on the oval window, and then it's a fluid disturbance and mechanical motion with the little hairs inside the cochlea, and eventually that turns into electrical signal. And all of that happens so ridiculously fast that you can't tell that there's processing time. And to me, that's fascinating. Okay, so I left you with 3 little questions to try. So section 10.1, if you could try 1, 3, and 4. And I said I would try and keep today short because there have been some other long lessons in this unit. So thanks for tuning in.